Hey guys, welcome back. In this video I'm going to go over properties of refraction and ray diagrams. So let's get into it. The first thing to look at is the definition of refraction. Refraction is defined as the change in speed of light as it passes from one medium or material to another, for example from air to glass or air to water or something else. So usually this also causes a change in direction, but not always. So it's a common misconception for pupils to think that refraction is the change in direction of light as it goes from one material to another, but it's not, okay, because we're going to see later on that it doesn't always change direction. We're going to see why we can't define diffraction as a change in direction, only a change in speed. The reason we can define it as a change in speed is because speed is always going to change when light goes from one material to another, but we cannot say the same for direction. So since light changes speed when it enters a new material, its wavelength will also change, but the frequency of the light remains constant. Okay, and to demonstrate the wavelength and the speed changing, let me show you a little animation. So if we have a look here, we've got a rectangular glass block and we've got light that will be coming in towards the block. So remember, light is a wave, and so we'll represent it as wavefronts, these straight lines. And I'll just play it a wee bit so we can see some of the waves there. So you'll see that from the source of the light, you'll see that these wavefronts are all separated by the same amount. And remember from the diffraction video that the distance between two adjacent wavefronts is the wavelength. So the wavelength is staying the same there. And so if I play the animation, you'll see that what's happening is all the waves are actually bunching up when they enter the material, and you'll see they spread out again as they leave the material. And when these waves enter the block, we can see two things happening. So we should be able to see that the waves slow down as they enter the block, so the speed changes, and the speed therefore decreases in this case. And we also see the waves bunching up closer together, so the wavelength also changes, the wavelength decreases. But because of the wave equation V equals F lambda, because the speed and the wavelength both change, that means that the frequency of the wave must stay the same. So we can say that the frequency of the light always stays constant no matter what material it's going into or leaving. And it's only the speed and the wavelength that will change, and the speed and the wavelength always do the same thing. So in this case, because we've got light coming from a less dense material like air into a more dense material like glass, it's slowing down and the wavelength decreases. And then when the light leaves the glass block, going from a more dense material, the glass, into air, which is a less dense material, then you'll see that the light speeds up and the wavelength also increases again. So going back to the notes now, we've kind of just shown that the light will change speed when it enters a new material, and its wavelength will also change, but the frequency of the light will remain constant. Because we're talking about different materials here, it's worth mentioning density as well, because we're going to be talking about light going from more dense materials into less dense materials and so on. So let's look at this. So it says how fast light travels in a material depends on how dense it is. The density of a material, which you'll probably already know, describes how closely packed its particles are, i.e. how much of its mass fits into a certain volume. So we could say that the more dense a material, for example diamond and glass, the slower that light will travel through it. And that is because of how closely packed the particles are inside of those materials. Whereas if you think about air, which is a gas, the particles are going to be moving randomly in all directions and are going to be spread out. So that means that light can travel faster in air, but it's going to be slower in the more dense materials. For example, glass is more dense than air, so light slows down when it passes from air to glass and speeds up again when it leaves glass, just like we saw in that animation earlier. I've also said here that air and glass are commonly used as the two mediums in refraction experiments. It might not always be air and glass, you might also sometimes see water for example, but speed of light in air I've given here as 3 times 10 to the 8 meters per second, and the speed of light in glass is a whole 100 million meters per second less than that, which is 2 times 10 to the 8 meters per second. However, other materials may also be used. So you will get this table in the data sheet of your exam, and it's there giving you the speed in different materials so that you don't have to remember them. So the speed in air is there at 3 times 10 to the 8, speed of light in glass 2 times 10 to the 8, but then you'll see the speed of water is 2.3 times 10 to the 8. So light travels faster in water than it does in glass, but it's still less than the speed of light in air. You'll also see we've got the speed of light in carbon dioxide, another gas, so it's still the same as in air, diamond 1.2 times 10 to the 8, and glycerol, which is that kind of gloopy liquid, which is 2.1 times 10 to the 8 meters per second. So next we're going to look at ray diagrams, and you need to be aware of certain terms. So we need to know the definitions of normal, angle of incidence, and angle of refraction. So the first one, the normal, it says here the normal is a dashed line that is drawn perpendicular at 90 degrees to any surface. The angle of incidence is the angle measured between the incident ray and the normal, and the angle of refraction is the angle measured between the refracted ray and the normal. So let's look at these in relation to the picture here. So what I've shown here is air and a glass block, and you've got an instant ray of light coming in. You've also got your normal drawn there. So the normal, we said, was a dashed line drawn perpendicular at 90 degrees to any surface. So there is my surface, and there is my normal, my dashed line, and you'll see that it creates an angle of 90 degrees at that surface. So that is my normal at 90 degrees. We then said the angle of incidence is the angle measured between the incident ray and the normal. So there is my incident ray, the light coming into the block, and there is my normal. So there is my angle of incidence, which I've called I. And lastly, the angle of refraction, that is the angle measured between the refracted ray and the normal. So there is the refracted ray, the ray that has changed speed and also direction in this case. And you'll see we have the refracted ray and the normal, so the angle between the refracted ray and the normal is my angle of refraction, which we've called small r in this case. Now, I've not extended this line through the block to come out the other side because we weren't interested in that here. All I'm trying to show you for now is the parts that explain the new terms that we're looking at. Lastly, we've got two important points down the bottom, and it says here, if light enters a new material and slows down, so it's going into a more dense material, the angle of refraction becomes smaller than the angle of incidence. And that is shown here. So we're going into a more dense material from air into glass, and you'll notice that the angle of refraction over here is actually smaller than the angle of incidence over here. And the opposite is also true. So if light enters a new material and speeds up, then the angle of refraction is larger than the angle of incidence. That's all for this video, guys. I hope you found it useful. If you did, give it a thumbs up, subscribe, and I'll see you in the next one. Take care.